morning all. So today we will discuss about ports. So in previous class we discussed components of Verilog module we have to discuss. So in that one there are divided into three blocks mainly. One is it belongs to module, then second one it belongs to module internals, and last one is end module, right? So here we have to discuss the first one, that is module. So module, in that module there is a what? Module name, module internals, and also very important one, list of ports, that is a declaration of ports. That ports we have to discuss here. Port provides an interface by which module can communicate with its environment. So why ports is required? Because it can communicate all the intermediate signals using these ports. Let us take one simple example, then you can easily understand the port. So here we know that IC, that is integrated circuits. There are many pins are available. That pins is usually what? Either input pins or output pins. So forget about what? The supplies, VDD and ground. But the pins are what? Either input pins or output pins. In that circuit, internal operation. So in that IC there are millions of transistors. All are what? It's not visible. So here also we can visible only input ports and output ports. We are not visible to what? Module internals. That is the what? Internals operation of the module. That is we call it as ports. So let us consider a list of ports. So next, let us take one example for a ports. So let us assume a full adder circuit, that is 4-bit full adder. So this is the what? A simple example for we have to define the what? List of ports. Here the 4-bit full adder circuit. This is the what? 4-bit full adder circuit. Here out of 4 full adders we have to assume one full adder here. So that name it as full add 4. So remaining are full add 1, 2, 3, 4. So you have to assume any one of the adder. So here you just observe the what? A ports here or inputs and outputs. A is the what? A input, B is the input, then Cn is the input, then sum and carry. So we call it as outputs. But all this what? We name it as a ports. One more block is there, that is we name it as top. So that we called as top level block. Here in this block diagram, in this block, top level module is instantiated the full adder. Okay. Top level module is instantiated the what? A full adder circuit. For the top level block there is no ports here, right? There is no inputs and outputs we have to mention here. There is no ports. So that's why we represent the terms of program can be written as module. It's always start with module. Then the name of the module is assume full adder. So here full add 4. Full add 4. So what are the ports we are? So A, B, C in and sum and carry. So A, B, C in, then sum and carry here. So these are all the representation of a list of ports, right? So next we have to consider one more level here, that is a top level block. So module top. Okay, why simply write module top? Because there is no ports here, right? There is no ports belongs top. There are ports only a belongs to full adder circuit. So this is the representation of a ports. So once you mention the list of ports, next we have to declare the ports. So here for ports in Verilog is classified into 3 types. So one is input, output, then in-out. So input acts as input port, then output it acts as a output port, then in-out. so it acts as a bidirectional port. So let us assume again 4-bit full adder circuit, then you can easily understand a port declaration. So let us assume with respect to previous one again, so module full adder 4 is the name of the module. So we know that for full adder, how many inputs and outputs? That is A, B, seen, then sum, comma, carry, right? So these are all the list of ports. So next we have to declare the what are all the input ports and output ports. So first we have to declare the input ports, that is input A comma B. Again A comma B, sorry, input 3 down to 0 A comma B. So we know that what do you mean by 3 down to 0? So it's an what? A 4-bit full adder circuits. So that's why both A and B it's 4-bit here. That indicates 3 down to 0. So next one we simply mentioned the carry in one, that is input seen. So input seen what? Single bit one. So next we have to declare the outputs. So output, so again sum is 3 down to 0, it's a 4-bit sum. So output sum is 4-bit. Then again after this one we have to mention one more, that is a carry one. So carry one is also an 1-bit one. So you simply mention the C out. So after this, so here some you have to mention the module internals. Then after this the end the module. So this is the declarations, it belongs to Verilog HTL. Again I repeat, so here let us assume a 4-bit full adder circuit, name it as full add 4, then these are all the list of ports A, B, seen, sum and carry. So input it's A and B, both are 4-bit, so that's why 3 down to 0 A comma B. Then carry in, it's a single bit one, either 0 or 1. So you simply write input seen, then output is it's an sum, it's 4-bit again, so 3 down to 0 sum, then again output is C out, carry out only what? A single bit, either 1 or 0. That's why we represent output C out. Then after this starting of the port declaration, so this is the ending of the port declaration. So after this you have to mention the logic, that is nothing but a module internals. Next you have to write module. This is the example for a 4-bit full add, that is port declaration. Here input ports as well as in out. So usually we access a nets or it's a wire, okay, but output should be acts as a resistor. Why output should be acts as a resistor? Let us take one more example, then you can easily understand output acts as a resistor. So let us assume sequential circuit for the a better understanding. So module, let us assume D flip-flop, DFF. So we know the inputs and outputs, we already discussed in previous classes, that is D is the input, then clock, D and clock, then we have to take reset is input, then Q. So these are all the a port declaration. Next you have to mention input and output. So input is, what is the input here? Input D, clock, then reset is the input, then you have to mention the output. So output is Q. So again I mentioned the output should be acts as a register. So after output you declare register Q, then these are all the module internals, then end module. So here you have to observe, you have to know the definition of sequential circuits. So what is the definition of sequential circuit? Output depends on the present as well as past. Again it depends on the variation of the what? A clock pulse. Means it operates a positive edge triggering or negative edge triggering. So that's why before going to the next state it should be stored or it should be retain the data. So that's why here the output Q it acts as a register again. That is we have to mention register Q. So this is the another example for the port declaration. So here one more style to represent the port declaration. So that's we called as ANSI, that is American National Standard Institute Okay, this is the another representation of a port declaration. So let us assume this example. So this is the what a normal Verilog representation. So this example let us write in terms of ANSI style. So that is module. So name of the module as it is module full add 4. Okay, that inside the module list of ports you have to mention first input 3 down to 0 A comma B, then after this input Cin, then output. So sum, that is 3 down to 0 sum, next one more output, that is output Cout. So next there is a module internals here, then end module. So here you just observe these two programming. So for this programming, first a list a ports. So that is A, B, C in, then sum and carry. After this list of the ports, you have to mention the what? A different inputs and outputs. But there is an advantage belongs to ECE technology, that is American National Standard Institute. So here you can directly mention the what? Inputs and outputs. Okay, that is an advantage here. Okay, that is you directly mentioned here input, then outputs here. Okay, so that is the one advantage. In your laboratory session you can write both the programming, it's not a problem. So usually we are using ANSI technology with respect to what? A Verilog HDL programming, that is in laboratory session. So this is the port declaration with respect to Verilog HDL. So in ports, in earlier we have to discuss what do you mean by ports. Next after this list of ports, so you have to mention what are all the available ports. After this you have to mention the port declarations, that is input and output. So after this there is a rules and regulations with respect to port connection, right? So there is a rules. Okay, we have to follow that rules. So here you just observe this diagram. This is called diagram for port connection rule. So here you have to mention the ports here, that is a in-out, input and output. So let us consider one by one. The input, first we have to consider the input is always, it must be a net. Okay, input is always should be a net and it should be connected. Okay, the input should be connected either register or net. Okay, again I repeat this, the input is always in terms of a net. Suppose internally, that is input is internally is always a net. Suppose it's connected externally, then at that time the external may be a register or net. That is the what? Input. Then let us take second one, that is output. Here for the output internally it should be a register or net. So it may be a register. For sequential circuit we call it as it register. Then for combinational circuit, so it's not required, we simply represent a net. So internally the output should be what? Either register or net, but externally it should be connected net only. It's not connected to with respect to a register. That is a output. Next, in-out. So in-out is what? It's a bidirectional port. Either it acts as an input port or output ports. So here there is a rule for in-out is the input is always a net, then externally it's connected is always a net. So that is the what? A port connection rules. So after this, suppose the port should be what? Unconnected. Okay, the port should be unconnected, and that time let us consider one example, then you can easily understand the what? Unconnected ports. Again we consider a full adder 4, then name it as simply F1. So here we know the inputs and outputs for full adder, right? So let us take one by one. Here first one. So during instantiation we always represent, the first is the output, then sum, then Cout, then Cin, then A, B. So this is the what? A representation during instantiation. So again when it is unconnected port, because sometimes the unconnected port is usually used for a debugging purpose. Okay, and that time this can be modified into full add 4 F1. So let us assume the C out is the what? Unconnected one. So on that time this can be written as sum comma here C in A comma B. Okay, so there is no what? C out representation here. So it's an optional one. So sometimes it required here. Okay, that is what? A unconnected ports. So next, so once you declare the what? Some rules and regulations of a port. Next, connecting ports to external. Okay, connecting ports to external. So here two methods for connecting ports to external. The one is a connecting by order list. So based on that order we are connecting to the external signal, and the second one is connecting ports by name. So let us consider one by one. So let us consider first one, connecting by order list. So here it's connecting by order list. It's one of the most easiest method to a beginners. There are two representation. One is a top level block, another one is a low level block, right? Let us take example again, full adder circuit, that is 4-bit adder circuit. So in top level block there is a what? A 4-bit adder. So in bottom level there are 4 full adders. So here for 4-bit full adder, so same we name it as a top. Okay, that in the top the outputs and inputs is same adder with respect to what? Module definition with respect to full adder circuits. So that is why we indicates connecting by order list. So the order of the what? A top block and as well as a full adder block, both are same. So let us take one example for this first one, that is a connecting by order list. So again we have to assume a full adder circuit, module top, input 3 down to 0, A comma B. Then again we have to mention one more input, that is input C in. Then after this you have to mention output. So output is 3 down to 0, sum. Then one more output is there, that is output C out. Okay, so after this input and output declaration we have to instantiate a top level module with respect to full adder circuits. So that can be named as full add 4, again same name is written here. Then name of instantiation we can write using this one, that is full underscore order list. Order list. So here be careful here. The observation is what? The first we have to declare the output, that is a sum. Then next C out. Next one more, that is A, B and C in. So after this there is some internals, module internals is there. Then after this then end module, right? So this is the representation of the what? A top level module. Next we have to write instantiation one, that is here, that is full adder 4. Here the representation order is very important one. So what is the order here? Sum, C out, A, B, C in. So same representation here, same order, that is sum, then C out, then A, B, C in. Same order. Then after we know that representation, input A comma B comma C in, then output sum comma carry. Then after this a module internals, then end module. Okay, this is the representation of connecting by order list. Again I repeat this. So here the name indicates connecting by order list. So both what we have to consider here, top down design methodology. So both again you have to consider a gate level netlist. So for the gate level netlist you have to assume module top is the name of the module is a top. So here name of the module for a design purpose, that is full adder 4. So first you have to write here. Okay, the obviously we know that input is 4 bit AB, then carry is only 1 bit, then output, then 2 output you have to mention here. Then after this is very important one, full adder 4 full underscore order list is what? Sum, C out, A, B, C in. So it indicates first you have to mention the outputs, then sum, C out, then after you mention the inputs. Then after this there is some module entrance, then end module. So after this instantiate here, top level block is instantiate what? A full adder 4, that is module full adder 4. Here the order list is very important one. Whatever order you mentioned here in earlier, you have to mention the what? A same order here. The first one is what? Sum, then C out, A, comma B, comma C in. So next we have to consider connecting ports by name. So let us take simple example for the connecting ports by name. So what is the difference here for the connecting ports by name? So in earlier we have to mention the what? Order list. Suppose there are 50 ports, right? So there are 50 ports. On that time it's practically what? It's impossible to represent what? All the 50 ports. So on that time that can be replaced by connecting ports by name. So if you want to declare the ports on that time, obviously there is a what? Error is created. Okay, and that time we are using better one, connecting ports by name. So let us take example for this one, then you can easily understand the what? A difference between connecting ports by name and connecting by order list. So let us take example. So directly we go to what? A instantiation. Full adder 4 ports underscore by name, that is the what we have to represent ports by name. In previous one we write by order list. So here we know that what are the inputs and outputs with respect to 4-bit adder? A, then name. So again you represent dot A. So comma B, then again you represent dot B. Again there is a sum, you represent dot sum. Then again after this C out, you represent dots C out. Okay. Then after this last one, that is C in, represent dot C in. Okay. This is the representation of by name. So here A, the name is what? A, same here. B, same name. Then sum, same name. Then C out, there is a same name. Then C in, there is a same name. So that is dot representation instead of this one, that is first one by order list. So here suppose you have to assume a one unconnected ports. So one port is not required. So on that time, so this can be modified full adder 4. Again same name, that is ports by name. So you just remove the what? Unwanted one. So let us assume C out is the unwanted one. You just remove that one. So A dot A comma B dot B, then sum dot sum. Then again, so here you remove the what? This one, that is A double comma then C in dot C in. Okay. So this is the presentation without a optional port. Okay, here we have just remove the what? Optional is C out, that is the what? A representation of connecting ports by name. So again I repeat this, what do you mean by connecting ports by name? So there is a disadvantage with respect to first one, that is a connecting by order list. Suppose there are 50 ports, on that time that practically is impossible to what? Assume the all the 50 ports. So on that time instead of order list we have to assume connecting ports by name. So here directly go to what? Instantiation. Okay. So all those things, module, input and output. So all are what? A same one. Okay. There is no change. Directly go to what? A instantiation, full adder 4 ports name. So here A dot A, then B dot B, same name here. Okay. Earlier the order is same, but here the name should be same. Suppose you have to assume unwanted port, the port is optional one, you just remove that port. So here let us assume C out is the unwanted, just remove the C out. So this is the what? A connecting ports to external. So last topic of the second module, hierarchical names. So in previous class we discussed about a different hierarchical design methodology, right? For example, top down design methodology and bottom up design methodology. So here we discuss hierarchical names. So the name indicates here hierarchical name refers a unique name. Okay, we have to provide the unique name for the all the identifiers. Let's take example for hierarchical names. So this is the example for hierarchical name. So we have to assume SR latch. So we know that SR latch circuit we already discussed, right? So here this is the what, a representation of the hierarchical name. So hierarchical name is stimulus, a dot. Okay, the dot is separated by hierarchical names and identifier. So here the identifier is what, a different ports. So let us assume here the stimulus is the, we name it as root level. So after this here SR latch we name it as M1. Okay, then after this SR latch requires what, a 2 NAND gates, NAND gate 1, that is we name it as N1, then N2. For root level we can't assume inputs and outputs, so that's why we represent in terms of variables. So variables are Q, Q bar, set and reset. So for SR latch we have to directly mention what, inputs and outputs, that is Q, Q bar, then SR. So this we called as a signals. So here next we have to write the what, a representation of a hierarchical names. So first stimulus, a root level name, so that is hierarchical name is what, a stimulus here, that is stimulus. Then representation of hierarchical name is, that is a dot symbol, hierarchical name dot a identifier. So here stimulus is the what, hierarchical name, that is stimulus dot q, the first identifier is dot q here. So that is stimulus and q is separated by a dot. So after this stimulus q bar is there, stimulus dot q bar, then set is there, stimulus dot set, then reset is there, then stimulus dot reset, then after this be careful here, that is what, M1, that is stimulus dot M1 dot, here what are the signals, Q, the first one is Q, then Q bar, then S and R. Again it's not completed, so here we have to represent what, a signals. Again you need to represent a N1 and N2, that is 2 NAND gates, that is stimulus dot N1 and stimulus dot N2. So this is the what, a second module. So in second module it's very important one. Why? Because of, so before going to third module, fourth module and fifth module, it belongs to what, programming. So before what, go to programming, we have to refer what are all the requirements for the programming. So what are all the requirements? It's similar to C programming. Some data types is required, some lexical convention is required, then also how to represent inputs and outputs, right? That is we call it as ports, and also we discuss a modules. So how to represent structure of the programming we have to discuss. Then after this you have to take what are the rules and regulations for the ports, then how to declare the ports, then how to connect the ports, then after this how to represent the what, unique object, that is hierarchical names. So these are all the what, it belongs to a module 2.